Okay, this is the notes for section 5.7, graphing inequalities in the coordinate plane. If you haven't done so already, make sure that you pause the video at this time, read the section before continuing on with the notes. Okay, so in 5.1 we looked at graphing inequalities on a number line. So we were looking at inequalities that involved one variable, whereas now we're going to look at graphing inequalities involving two variables, in which we're going to have to do that on a coordinate plane. So when we draw a line in a plane, the line basically takes a plane and it separates it into three distinct sets of points. Remember, coordinate plane is it's sets of points that we're looking at. So the two regions are the half planes, and then we say the line itself is the boundary of that half plane. So the three regions are the two half planes and the boundary separating those half planes. Okay? Okay, as I mentioned before, 5.1 is where we kind of looked at graphing inequalities with one variable, and we were able to do that on a number line. We can also graph inequalities with one variable on a coordinate plane as well. So for instance, if we wanted to graph the line, graph the y is less than 5 on a coordinate plane, that would represent all the ordered pairs, xy ordered pairs, such that the y value is less than 5. So if we were going to graph that, we'd graph a horizontal line at y equals 5. It'd be dotted or dashed because 5 would not be included in that solution set, and then it would be all the values of that are underneath that horizontal line. Okay, we would shade those values in. Okay, and that shaded region would represent the set of points x, y, or ordered pairs such that y is less than 5. Okay, most of the graphing that we're going to do in this unit in this section I should say, involve graphing a boundary that is an oblique line, neither horizontal nor vertical, but it's going to have both an x and a y value in the inequality for that line. So let's look at number 1 here. It says graph the linear inequality y is greater than or equal to 2x plus 7. Okay, so to do that, what we're going to do first of all is we're going to graph it as if that inequality were an equal sign, and graph that line that you would get for y equals 2x plus 7. So I'm going to use the y-intercept of 7, and I'm going to use the slope of 2 to graph that line. So I graph that line. I have my y-intercept here of 7. Okay, I'm using a slope of 2 up 2 over 1, or you can think of it as down 2 over 1. So I've got my line graphed. Now notice how I graphed it as a solid line. The reason why I graphed it as a solid line is because I know it's greater than or equal to. So that means that the boundary is included in our solution set. Okay. Now the next thing we have to do is we need to determine where we're going to shade. Okay. And to do that, what we're going to do is we're going to look at since it's already in slope-intercept form, basically, the y values are greater than or equal to 2x plus 7. So that means we're going to graph above that line. So as you look at it from left to right, as I'm going from left to right, above the line would be above and to the left here. So that's the area that I'm going to shade. So that would represent, once I've shaded in that area, that would represent the solution set to the inequality y is greater than or equal to 2x plus 7. Now all of the ordered pairs that are in the shaded region, so that half plane plus the boundary line, would all be members of that solution set. Okay, so let's take a look at number 2 then. It says, is the set of points satisfying 4x plus 3y less than 8 above or below the line with the equation 4x plus 3y equals 8? Okay. Well, first of all, let's graph that line. So what I want to do is, since it's in, we're graphing the boundary line, which is 4x plus 3y equals 8. So I'm gonna use the fact that since it's in standard form, I'm going to use the intercepts to graph that. So when x is 0, or excuse me, when y is 0, x is 2, and when x is 0, y is equal to 8/3. So let's graph those 2 points and then draw in that line. Now that boundary line we know is going to be a dotted line because it's less than, not less than or equal to. So here's that line. You'll notice that I have the 2 intercepts here at the point 2, 0 and the point 0, 8/3, which is approximately 2 2/3. Okay, so I've got that line drawn in. Now I want to decide, is it all the points above or below that line? Well, if it's not solved for y, sometimes that's a little bit harder to decide. But the easiest way to do it is to pick a point in one of the half planes. It doesn't matter which one. Okay, either down in this one over here or above the line. And then decide which ones are going to satisfy that. Well, if I get a true statement when I plug that point in, then I'm going to shade the half plane that that point is in. If I get a false statement, I'm going to shade the other half plane. Well, the easiest point to pick, if you can, if it's not on the boundary, is 0, 0, which in this case it's not on the boundary. So if I plug 0, 0 in here, 4 times 0 is 0, 3 plus 3 times 0 is 0. So the left side is 0. Is 0 less than 8? The answer to that is yes. Therefore, I'm going to shade the area that is below the line, or below and to the left of that line. So the answer there then would be all the values that are below the line. And then I've shaded in that area here on this graph. Okay, the last new idea I'd like to look at in this section is the idea of lattice points. Now we talked back in chapter 3 about discrete domains, and we know that sometimes we limit our domain and limit our range to integer values. Well, when we're dealing with inequalities and we limit our domain and range to integer values, what that means is that we end up with a solution set that is only integers, and therefore we call them lattice points. Okay? If there are not too many lattice points in the solution, you should indicate each with a dot on the plane rather than shading the entire region. So if you have a smaller solution set, one where you can relatively easily put in the dots of the solution set, you should do that. Okay? Okay, finally let's take a look at number 3 here. It says a ferry boat carries cars and buses across Lake Michigan. The boat has space for 12 cars and a bus takes up the space of 3 cars. Draw a graph showing all possible combinations of cars and buses that can be taken in one crossing. Okay, well, the first thing I want to do is I want to assign variables. Well, I know that I'm looking for cars and buses, so the two variables that I'm going to have is C is equal to the number of cars and B is equal to the number of buses. And then I want to write an inequality using those variables. Well, the number of cars plus the number of buses is got to be the number of spaces taken up is 12. So I'm going to have the number of cars plus each bus takes up 3 spaces. So I can say the number of cars plus 3 times the number of buses has to be less than or equal to 12. Okay? So the next thing that I want to do to come up with my solution set is I'm going to graph that line as if it didn't matter if they were whole numbers or not. When I do that, I have my line drawn in here. Okay? I started with my intercepts of 12, 0 and 0, 4. Draw in the line. Now, I know that when I'm looking at my solution set is only those values of whole buses or whole cars. So I need to have integer values. So I'm going to have lattice points here. So when I do this, when I graph these points, I'm going to graph each of the integer coordinates that are below that line. So all of these red dots would be members of that solution set. And it would represent kind of that reasonable amount of dots to put in, so you don't have to, instead of shading, it's a better idea to actually graph those lattice points, and we get a much better idea of what's going to happen with those buses and cars in terms of how many of each we could have on that crossing.